Okay, so let's get started with the first speaker, Matthias Ehrhardt from University of Bath, and he will tell us about structure preserving deep learning.
Thank you very much, Johannes, for the very kind introduction, and thank you so much for the organizers for inviting me. Yes, I indeed want to talk about structure preserving deep learning, and before I go into the topic, let me also mention that this joint work with a number of people. A couple of them also like in the audience, sort of like in Cambridge. So I think I've seen Martin Benning already, but also there's Christian Edman and Carola Schönlieb, I think, who was also there today, and Ferdia Sherry, all from Cambridge. And but it's also joint work with Elena Caledoni and Brynjulf Oren from NTNU Norway in Trondheim, and Robert McLachlan from Marseille, New Zealand. Okay. So what are the main messages of the talks? And so here I would like to talk about deep learning and how it connects to kind of like other fields or like of the fields of mathematics, and how we can put guarantees in there. So we would like to connect deep learning to some continuous modeling, and this may offer insights into the structure of deep learning. So we can connect it to things like optimal control, differential equations, in particular numerical differential equations, constrained optimization, and so on. And by making these connections, we then will be able to have deep learning with some guarantees. So deep learning which is provably stable, where the network may be invertible, equivariant, where the data may live in a manifold, and so on. And very important also to mention that there are like many open problems and interesting opportunities for the mathematical community to contribute in this direction. Okay. So we have kind of like worked on this in like a number of directions. So we've recently written a review paper, that's here like the first one, where we go into more detail on like 5 different topics that all fit into this scope. And so which are like related to like neural networks inspired by differential equations, equivariant neural networks, invertible neural networks in their relation to normalizing flows, deep learning and the connection to optimal control when you want to learn it, as well as structure exploiting learning. But today, due to time constraints, I only will go into detail for the first 2 topics. But like if you're interested in the other 3, please check out the paper number 1. Okay, so let's set the scene. So what do I mean with deep learning? So we're talking about neural networks. And so neural networks here usually are denoted by letter phi that may depend on parameter theta going from spaces x to y, and we define this recursively such that whatever input we have is mapped to zk, where zk is the case iteration of this recursion, where always we take the input from one sort of like layer and sort of like map it through a potentially nonlinear function fk, and we get the next zk plus 1. And these fk's, in general, they may be like generic layers, just like mapping some parameters and input to some output. But sort of like sometimes we also then consider special cases. A special case of this generic layer are fully connected layers that, for instance, could be of this form. So we have an input, which is a vector. We have some parameters, and then the output is an affine transformation of the input, and then some nonlinear function applied to it. And like this nonlinear function, sigma, might be like the ReLU, the hyperbolic tangent, and so on. But for us, it's like not very important at this stage what it is. A can also be something that is not a full matrix, so it can be like a convolution operator and so on. And then the training goal in deep learning is, or in supervised deep learning, when you have given some training data x and yn, we want to minimize the cost function, so we want to map the xn as close as we can to yn under some sort of like some cost, and we potentially also want to regularize the parameters in some way. And so what's the problem with deep learning? So like there are many successes of deep learning, as you all know, but then there are also a couple of problems, at least with the networks that are commonly being used. So 2 of the problems that you see in the literature is, on the one hand, that they might not be robust to noise. So if you have an image and you want to classify it, so here's correctly classified as a panda, and then you add some noise to it that is invisible to the human eye, this might completely change its classification, right? So we humans would never be fooled by this noise, but deep learning is fooled. Likewise, if you have an image here, in this case of a vulture, and then so you rotate it around, this might change its classification completely. But obviously, sort of like a vulture that has been turned around by a few degrees, I mean, should not change, like get a different class label, right? So like ideally, we are robust to noise and we are robust to rotations, for instance, in classification. And so the standard strategy that you see in the literature is called data augmentation, where you just like take a certain perturbation under which you want to be stable. For instance, this could be noise, it could be rotations, this could be whatever. And so you can sort of then like artificially change your data and give it kind of the same class label or the same desired output. And thereby you may hope that your neural network becomes stable with respect to these perturbations. And this is called data augmentation. So in this talk, we want to have a different route to kind of like get stability with respect to, for instance, noise and rotations. And this is, we want to like to change the deep learning architecture such that they actually provably have these guarantees. And so, for instance, if we have a certain type of continuity, then sort of like the noise can't change the class label so easily anymore, as well as if the neural network is equivariant or invariant, that means that sort of like whenever that you like rotate it, then you would still get the same class label out, guaranteed. You know, this like doesn't matter how the network has been trained. Okay. So the first thing I would like to talk about in detail is neural networks inspired by different equations, and this then will be related to the stability aspect, the aspect of what happens when we add noise, to the images. Okay, so on a few slides ago, like I was talking about sort of like some classical kind of fully connected neural network of this type, but then there are other neural networks which you commonly see in the literature. One of them is so-called the ResNet, the deep residual neural network, where instead of having this sort of like affine transformation, the nonlinearity, you also add sort of like a copy of the input of the nonlinearity to it. And so then here now, sort of like I added another scaling factor, but like you can also choose the scaling factor equal to 1. So this is called the ResNet. It's being used a lot in the literature. Sort of like as a site here, sort of like as of yesterday, it has more than 85,000 citations, this paper. And when I last time gave this slide, that was I think in February this year, sort of like it was 68,000. So like within like half a year, that paper got cited another about 20,000 more times. And when you, as a mathematician, look at the ResNet, then you might think, oh, this looks very familiar. This is like nothing else than the forward Euler discretization of a certain ordinary differential equation, right? So now we can connect the ResNet to a differential equation, but we know how to handle differential equations. So we might be able to kind of like say a lot of things about the continuous model, and hopefully then also can perhaps then derive some stability, for instance, for the ResNet based on this. Okay, so here is the ResNet in action. And so this is a type of picture that is very uncommon to see in deep learning, but it's very, very common when you think about ODEs. So like ODEs, they very naturally like describe a flow. And so here on the left-hand side, we have the training data. So each of these dots is a training data point, and then the color indicates like the class label. And so here are like two different data sets. And so here the different images show the flow of the learned network as you propagate through the layers. So we have some topology that can't be really linearly classified, and we want to classify it along this gray decision boundary. And so then the flow through the neural network is kind of like really trying to separate these things. And in the end, you get like two clouds, which you can very, very nicely linearly classify. The same is true here for this donut data set, where you kind of need to fold things a bit in order to work well. Okay, by making this connection between neural networks and differential equations, therefore kind of like the supervised deep learning training problem, then like its continuous counterpart is nothing else than an optimal control problem. And again, this is like another of these things that we mathematicians know quite well, and sort of like there has been like decades of research to study these things. And so what are the advantages of thinking along those lines? On the one hand, it's very concise. So we can write down the training problem in deep learning in just 2 lines. The continuous analog can be used in order to propose new architectures, new discrete architectures, by discretizing it in different ways. As I said before, continuous models also, there are kind of like simple, and we can actually mathematically analyze them. So we are actually, it's much easier to say something about the continuous counterpart usually than about the discretized system. But then the question in the end is like, whatever continuous properties we prove, will these be preserved by the discrete or discretized neural networks? That's obviously then like an open problem that one needs to address separately. And so kind of like this connection sort of like has first been done by Ehrhardt and Lars Rutotto, as well as a group around Wayne and E in 2017-18, and many people then have picked up on this subsequently. Okay, so in order to be robust with respect to noise, we probably want to talk about stability. But like now the question is stability in what sense? When we talk about ODEs, there are many different notions of stability around. So there are stability around equilibrium points, which are then related to Lyapunov stability or asymptotic stability of autonomous systems, for instance. We can also ask, how does the trajectory change when we change the initial value? We can think about stability either on a finite time horizon or an infinite time horizon, and so on. From a neural network point of view, the questions of stability are probably a bit different. So there, usually one is talking about Lipschitz continuity of the neural network. And one thing to note is that most of the used neural networks, they are all Lipschitz continuous, no matter how you've trained the data. However, the Lipschitz constant of the network is usually sort of like depends on the data, and in general might be arbitrarily large. So like practically sort of like you have a useless Lipschitz constant, although you are technically Lipschitz continuous. So therefore, like instead, what some people want to do is they want to train the neural network such that you satisfy a specific Lipschitz constant, for instance, 1, 7, whatever, and which kind of like is not allowed to grow arbitrarily large. So in the first time, sort of like this connection between sort of like ODEs, neural networks, and stability has been looked at was by Ehrhardt and Lars Rutotto in 2017-18. And so they make the connection to sort of like to the theory of autonomous ODEs. So we have an autonomous ODE, and then this is asymptotically stable if the real parts of the eigenvalues of the Jacobian are non-positive. This is a very classic theorem you see in plenty of textbooks. And so like for the ResNet, what this means is, so if the nonlinearity is monotonically increasing, then the forward propagation going through the network is asymptotically stable if some condition on the eigenvalues of the linear part sort of like is non-negative. And so here are is non-positive. And so here are some examples. And so these are like super classical. Sometimes you see things are like blowing up. Sometimes they're contracting. Sometimes they're rotating around. And with this in mind, they then came up with new neural network architectures which have this eigenvalue condition already implemented, built in. So like no matter how you train the network, you always satisfy this condition. So you can have, for instance, like the ResNet with an antisymmetric transformation matrix. You can also have Hamiltonian inspired networks and so on. So a problem with this line of argument is that these arguments are really only true and like really useful if you have autonomous systems, which means that your mappings are not, that your right-hand side, your vector field is not changing with time. But that's not really true in deep learning, and we actually want to have the flexibility to adapt the neural network accordingly. So you can extend the theory a little bit to non-autonomous systems, but then the theory becomes rather weak and you get rather complicated sort of criteria that you like assumptions that you have to satisfy in practice, which are all rather shaky, I would say. So here we would like to look at a different line of mathematical arguments, how you can actually have stability. So here we want to follow basically the neural network stability sort of definition, where we want to have, we call it neural network stable if it's actually Lipschitz continuous in its inputs. And so one way of arguing when you have this is, so if the right-hand side is the vector field of the ODE, if that is Lipschitz continuous, then we always have that flow is also Lipschitz continuous, and we can have estimates on the Lipschitz bound of this form. But this form is not very useful, right? So like it's e to the t times L, where t is the final time, and L is the Lipschitz constant of our vector field. But since t in general might be greater than 1 and potentially large, L might be greater than 1, potentially large, e to the product of that is even larger, so that is actually quite a large number, so that might not be very useful. Then on the other hand, we can do a similar arguments based on what's called like the one-sided Lipschitz continuity. And so that is a concept very well established in ODE theory. And so like if the vector field satisfies this condition, and now the catch is that sort of the one-sided Lipschitz constant nu, this may even be negative, then you can prove basically the same Lipschitz constant, or the same formula for the Lipschitz constant of the final flow, but then this nu may be negative. So you actually may have that it's not only is Lipschitz continuous, but also even it's non-expansive or even contractive. But now the question is kind of like, how do you even design vector fields such that you have actually like this negative one-sided Lipschitz condition? And it turns out this like has been studied before, obviously. And so, for instance, like if we have a potential which is twice differentiable and convex, and our vector field is a negative gradient of this potential, so we have like a negative gradient flow, then this satisfies the one-sided Lipschitz constant with some non-positive Lipschitz constant. So that's great. And then like likewise, sort of like we can have something like a ResNet, but then it's a modified ResNet where we have the adjoint of A appearing, and so like this one also kind of like is the gradient flow of a certain system, and so like this is a special case of the thing before, and we have that the overall thing is non-expansive or even contractive. So what is great about this a lot of arguments is also that it doesn't require any smoothness of this mapping A that goes from 0 to t to the parameters. So like this can actually vary as much as I want, as long as for each of the time steps this is satisfied. And also there is an analog for discretized systems. So for instance, in the context of explicit Runge-Kutta methods, Dahlquist in the 70s, he proposed what's called a circle contractivity condition, which kind of like looks quite similar, but it's also like a bit different to what we have before, because I mean, the right-hand side is different. And then we can even prove some non-expansiveness of a discretized neural network, not only of the continuous counterpart. Great, so here are some numerical examples how all of this looks like in practice. So here we compare 4 different Runge-Kutta methods, which all discretize the same continuous ODE. And we want to classify this like spiral example. And what we can see here, as we vary the discretization, sort of like all of the classifications are pretty good and they all look pretty similar. And as well, so here at the bottom, we can see kind of the flow of the final point of the flow of the points, as well as with the linear classifier. And again, also this one looks quite similar. So like for this example, we can't really see like much of a benefit by like discretizing the continuous ODE with different methods which are potentially higher order. Another nice thing about when you have this continuous ODE in the back, that this might motivate different parameterizations of the neural network. So for instance, so like if we have kind of like this update equation, so like the standard ResNet, you either kind of choose kind of like this update delta t equal to 1, or you might choose it sort of like equal to the final time divided by the number of translation points. But then sort of like it's very natural to come up with 2 more kind of like neural networks. One of them that we call kind of the ODE net, where you learn the update steps. So like this can be like any real number. And another one is basically the same as the ODE net, but in addition you have a simplex constraint. So all the time steps are non-negative and they should integrate to the final time t. And so this is how it looks like in practice. So like the kind of like classification you get is a bit different. So here the ODE net seems to be doing the best when you have this extra degree of freedom in it. But also what's interesting is that the final transformation that we learn here also looks quite different. So like the ResNet and the ODE net plus limit constraint, they look quite similar. Whereas for the ENet, sort of like the data is transformed in a way such that the data in the end kind of very nicely lies on a on a one-dimensional manifold with the linear classification really separating the linear manifold on two lines, one of them being blue and the other one being red. So looking at the time steps which are being learned is also quite interesting. So that the time steps of the ODE net actually they may become negative, as you can see here in yellow, and for the simplex constraint, as what we can see here in purple, or actually it turns out that only 2 of the time steps are non-negative. So although we started with a network that potentially has 20 layers, only 2 of them are actually active in the end. All right, let's for the remainder of the talk a bit about equivariant neural networks. And so what I mean by this? So like, for instance, here we want to learn a neural network that is denoising images. So our noisy images look like this. And now we train neural networks that kind of remove the noise. And we either train sort of like a standard convolutional neural network, and one which is kind of like equivariant with respect to some rotor translations. And so both of these networks that perfectly well are capable of removing the noise in the network. But now if we, in like all the training data, these all are horizontal lines. If we now apply this learned neural network to test data, which has now vertical stripes, we can see that if we just have convolutions without any additional equivariance attached to it, we then like ruin the structure. As we can see, kind of it tries to smooth horizontally because kind of it overfits to the training data, whereas the equivariant one sort of like nicely preserves the structure and gives us those rotations. Oops, sorry for that. Okay, so mathematically, so like what do we mean by all of this? So if we have like a group which acts on 2 spaces, and we denote how it acts by sort of like gx circle y and gy circle v, then we call a mapping phi from x to y, we call g equivariant. If for all group actions g and all elements u and x, we have that basically in some sense the group action kind of like commutes with the mapping phi, but obviously kind of like it's a potentially different group action on the domain and the range of phi, right? Because these are like different spaces. And so if the phi is g equivariant, and if gx trivially on y, meaning kind of this guy here disappears, then we call it a g invariant, right? So if like however we like transform the u kind of like in x, then it's like phi of that transformation is the same as phi of u, right? That's g invariance. And so examples of interesting groups are, for instance, translations, and then you come back to kind of convolutional neural networks, the rotation scalings, or in this work we will particularly look at rotor translations, where the group action kind of like has 2 components, it's translation and a rotation. And when you apply this to a function, to an image, then we, on the one hand, we rotor translate the function on its domain, but also kind of like if the function output is, for instance, like a vector field, we may want to rotate that vector field as well. And so this concept of group equivariance or invariance has been studied a lot for image analysis tasks. And so I mean, sorry, many authors kind of like have made great contributions. Probably one of the people who made the biggest contributions are probably Cohen and Welling, but many others did also do great contributions in this regard. But now, if we have this abstract concept and we want to get G equivariant neural networks, the question is, how do we even get this in practice? And it turns out that there's a fairly rich toolbox of what is and what isn't G equivariant. So first of all, if we have 2 G equivariant operators, then their composition is also G equivariant. If we have 2 G equivariant operators, then also the sum is G equivariant, as well as the identity operator is trivially G equivariant. And then sort of like when talking about what are G equivariant, for instance, linear operators, how do we parameterize them, then it matters a lot, kind of like what are the groups of interest. And so if we are, for instance, like in this rotor translational group, then sort of like one can fairly easily show that there are non-trivial G bar equivariant linear operators. I will show them on the next slide. And you can also show that there are G bar equivariant nonlinearities, and also sort of like biases, they can become G equivariant if there are if the bias is G invariant. And so having all of these building blocks, we can then like put this together, and so we can have like the same layered structure, like if each of the layers is G equivariant. Then sort of like the final output is G equivariant. We can have the standard network as well as the RESTnet and so on. So kind of like this on this slide.
Yeah, there are 5 minutes left for your talk.
I know. Thank you so much.
Okay. Sure.
So on this slide, I want to talk a bit about sort of like how to get linear operators which are G bar equivariant. And so kind of like in a nutshell, so G bar equivariant linear operators are convolutions where the kernel satisfies some additional constraint. And so more precisely, so if the linear operator is an integral operator, then this integral operator is G bar equivariant if this kernel actually sort of like is translational invariant and is rotational invariant with respect to all the rotations that we want to consider in our group. Okay, so now applying this to some fields where sort of deep learning has made an impact. So for instance, what if we want to use neural networks in order to solve inverse problems? So like since inverse problems usually they map from between two different spaces, X and Y, the solution operator also goes from Y to X, but these are like have very different properties. So some of them might be images, others may not. So therefore, like it's not clear sort of like what kind of equivariance properties such a neural network should satisfy. But you may want to ask, what if this neural network composed with a forward operator, whether that is equivariant? And then it turns out, in generally, this is not equivariant. And the problem is that if the forward operator, for instance, has a kernel, is not equivariant, it's very difficult that their composition becomes equivariant. That being said, a very important component of how to solve inverse problems with neural networks actually can be made equivariant, and these are proximal operators. So if the group acts unitary on the space, and if, for instance, so we have a functional J, which is G invariant, and this prox is well-defined and single-valued, then the prox is actually G equivariant. And so kind of like this now motivates the use of equivariant neural networks wherever traditionally we would have used proximal operators. And so this proof also generalized to kind of like a bit more broadly to sort of like what's called variation regularization, where we have a squared L2 data fit, but only if the forward operator A is equivariant, and sort of like that is often not the case, for instance, if you have a non-trivial kernel. All right, so like this, so like how, like what happens in practice. So like now we have like two neural networks where some of the components, so like here with the ordinary one, they're just like translational equivariant, and the what's called here labeled equivariant, they are rototranslation equivariant. And when solving some CT inverse problem, we can see that sort of like that having these rototranslations really can make a big gain in practice. They're sort of like a much better defined images. And also sort of like when looking at this more like quantitatively, you observe that overall the equivariant neural network works better, but the biggest difference is really on small training data sets when you kind of like impose structure on the neural network that you don't have to learn from data. So with this, I would like to conclude the talk. So I would like to make the point that continuum modeling of neural networks really opens the toolbox of many mathematical and numerical analysis aspects, which can then be translated to deep learning. We've seen connections of deep learning to ODEs, optimal control, and group theory, and there are like many other aspects that I couldn't touch upon in this talk. And so we can like design neural networks which have mathematical guarantees by using a certain structure, like stability and equivariance. And this really opens many interesting, exciting questions where mathematicians can help in designing new deep learning networks or analyzing them. Thank you very much for listening.
Yeah, thanks. Great talk, Matthias. Other questions? We have time for one or two questions. Can I start maybe with one question? So it's a very basic question. So you defined the RESTnet, and you also have this small picture, but isn't it that maybe you can go back to the slide, isn't it that you then also in this original RESTnet formulation, you would also put another activation function before you, so around the zk plus delta t blah blah blah, you also put another look at the small picture. So you pass the identity, you add it, and then you add to the sum the activation function another time, but you don't do that in the Euler discretization scheme, right? So isn't there a difference? And what does it matter for the implementation?
Fair enough. Good question. I'm not so sure on the implementation point of view how important this extra nonlinearity is. But it's true that sort of like in order to make the connection to ODEs, so sort of like you would need to choose this nonlinearity equal to the identity. Yeah, very good observation.
Okay, yeah, and then also something. So for the ResNet, it doesn't matter what like the weight metrics in one layer can be completely different than the weight metrics in the next layer, and so. But if you go to the discretized scheme, somehow they all have to be somehow close, because it's. I mean, A of t should be close to A of t plus 1 or so.
Well,
and so it's.
So I would say like this I mean like depends how you argue. So like with the arguments that I presented earlier, sort of like this mapping A needs to be smooth, and so like that kind of like implies that A of t is close to in some sense of A of t plus 1. With the other line of arguments, you actually don't need this at all, right? So actually A can be discontinuous, and it doesn't change stability, as long as sort of like for each of the time steps, sort of like you have this kind of like gradient flow structure, but then sort of like for each of the time steps you might have like a different gradient flow in very different directions, which then means that the mapping A is actually discontinuous. But this is not a problem for theory, interestingly.
Okay. Are there more questions? We have time for one more question. We can be a bit late, I think, today.
One in the audience. Ooh. Can you hear me?
Yes, I can.
Hear you.
Hi, Matthias. Thank you for the great talk. Quick question. You mentioned at the beginning. You mentioned the Lipschitz continuity aspect for the continuous models, and then you mentioned that there is this result for Runge-Kutta networks, this sort of 1979 result, I think. And I was wondering, can you comment a bit more on, like, first of all, you mean by circle contractivity and what the actual conditions are? Because I cannot see how for arbitrary, let's say for a forward Euler method, without additional conditions on, let's say, the Lipschitz continuity or conditions on the operators, that you actually get anything like this. So can you comment a bit more on this?
Yes, exactly. So like, so there is this is kind of like this parameter nu in here. And so this parameter nu, as well as sort of like so each of the explicit Runge-Kutta methods, for instance, with positive weights, they have like an associated condition that needs to be met. But it turns out that sort of like for each of the explicit Runge-Kutta methods with positive weights, so that there exists a step size such that you always have this continuity. And sort of like, for instance, for the explicit Runge-Kutta method, that kind of tells you sort of like that the time step needs to be small enough, depending on sort of like how much your vector field is varying.
Okay, thank you. Yeah, that's what I thought. Cool.
Okay, yeah, thanks, Matthias, for the
Thank you so
talk
much.
and answering the questions.